Why the SR-72's hypersonic speed breaks every rule of aircraft physics. The aircraft you are about to hear about should not exist. For decades, aerospace engineers accepted certain limits. Heat, drag, and structural stress formed invisible walls that even the best fighters could not cross. You could go fast for a few seconds, maybe a minute, and you had to slow down before the airplane started tearing itself apart. Then Lockheed Martin began testing something called the SR-72. Not a drawing, not a rumor, but a real machine built around one obsession: speed. Not quick bursts of speed or sprinting and backing off, but sustained hypersonic flight where air itself becomes the enemy. If the SR-71 Blackbird rewrote reconnaissance history, the SR-72 is trying to rewrite the physics textbooks that explained how the Blackbird worked in the first place. For years, speed always came with compromise. Aircraft could push hard, but only briefly. Heat would rise, engines would suffer, materials would weaken. Hypersonic research existed, but mostly inside missile programs that never needed to return home. The idea of an aircraft that could fly at Mach 5 and survive was treated as theory, not something that could actually operate in the real world. The SR-72 changes that idea completely. It is designed to take off, accelerate past Mach 5, complete a mission, and return intact. That sounds simple when spoken out loud, but in reality, Mach 5 means temperatures that can melt metals, airflow so violent it tries to rip surfaces off the aircraft, and engines that normally stop functioning long before reaching those speeds. This is why many engineers once called this impossible. Problem is not just going that fast. Problem is surviving it. And the story of the SR-72 is really the story of how engineers stopped fighting speed and started designing an aircraft that could live inside it. At normal speeds, air is something an aircraft moves through. At hypersonic speed, air turns into something the aircraft has to fight. Once you pass Mach 3, airflow stops behaving gently. It compresses violently against the front of the aircraft and heats up to extreme levels before it even touches the surface. By Mach 5, that compressed air becomes a wall of superheated pressure trying to push back on every edge, every seam, and every intake. The aircraft is no longer slicing through the sky. It is forcing its way through a barrier that gets hotter and harder the faster it goes. This is where most aircraft designs fail. Traditional jet intakes rely on slowing air down before it enters the engine. Shockwaves form, move, and sometimes become unstable. At high enough speeds, those shockwaves can cause engines to choke, stall, or lose power completely. Control surfaces also begin to lose effectiveness because the air flowing over them behaves unpredictably. Small changes in angle can cause massive forces that stress the structure. This is why fighters never stay at extreme speed for long. The physics becomes hostile. The SR-72 was designed with this hostility in mind. Instead of treating airflow as something to manage after the fact, engineers built the entire aircraft around how air behaves at hypersonic velocity. The shape of the body, the placement of the intakes, and the angles of the surfaces are all designed to control shock waves rather than suffer from them. At Mach 5, shock waves are not a side effect. They are part of the design. The nose and leading edges are shaped to guide compressed air in very specific paths, preventing pressure from building in dangerous places. Intakes are designed to handle air that is still moving at extreme speed without losing stability. The aircraft does not try to slow the air down the way normal jets do. It accepts that the air will stay violent and uses that energy instead. This is the first major reason the SR-72 feels impossible. It does not behave like a faster jet. It behaves like a machine designed for a completely different environment, and this environment is brutal. Air friction at these speeds creates temperatures high enough to weaken most metals. The pressure tries to peel layers off the aircraft. Even tiny surface imperfections can create massive stress points. That is why hypersonic missiles are easier to build. They only need to survive for a few minutes. They do not need to come back. The SR-72 has to survive every time. So instead of avoiding these forces, the aircraft works with them. Its structure distributes pressure across the body. Its shape keeps shockwaves stable. Its materials are chosen specifically because they perform better when exposed to intense heat rather than failing under it. This is where the real shift happens. Engineers stopped asking how to protect the aircraft from hypersonic airflow and started asking how to build an aircraft that belongs in it. That change in thinking is what makes the SR-72 possible. The biggest problem with Mach 5 flight is not the airframe, it is the engine. Traditional jet engines are built around one simple rule: slow the air down, compress it, mix it with fuel, and burn it to create thrust. This works perfectly at normal speeds. It even works well at supersonic speeds. But as velocity increases, this process begins to fail. At hypersonic speed, air is moving so fast that trying to slow it down creates chaos. Shock waves become unstable. Pressure builds unevenly. The engine can choke or stall because the airflow it depends on becomes unpredictable. This is why most aircraft engines simply stop being useful long before Mach 5. Missiles solve this by using rocket engines that carry their own oxygen. They do not rely on air at all, but rockets burn enormous amounts of fuel and are not practical for reusable aircraft. The SR-72 does something different. It uses what is known as a combined cycle propulsion system. Think of it as two engines sharing the same body and switching roles depending on speed. Now, it's way. Takeoff and low speeds, the engine behaves like a normal turbine. It pulls in air, compresses it, mixes it with fuel, and produces thrust just like a standard jet. This allows the aircraft to operate from normal runways and accelerate through the lower speed range. But as the aircraft gets faster, something remarkable happens. Instead of forcing the turbine to handle air it was never meant to process, the system reroutes airflow into a different path. This path leads to a scramjet, an engine that works on an entirely different principle. In a scramjet, air is not slowed down before combustion. Fuel is burned while the air is still moving at supersonic speed through the engine. That idea alone is why engineers once called this impossible. Burning fuel inside air that is already traveling faster than sound creates enormous challenges in stability and timing. Combustion has to occur perfectly, or the engine fails instantly. For decades, this only worked in experimental labs and missile programs. The SR-72 is built around making it work reliably in an aircraft that must return home. As speed increases, the turbine becomes less important and the scramjet takes over. The aircraft transitions from one engine mode to another without the pilot even noticing. What starts as a normal jet becomes a hypersonic engine in mid-flight. This allows continuous acceleration past speeds where normal jets would fail completely. But there is another benefit to this system that most people miss. Because the engine is not fighting the airflow, it does not generate the same extreme heat spikes that traditional engines would at those speeds. The airflow remains stable. Combustion remains controlled. The aircraft can stay at hypersonic speed without destroying itself from the inside. That is the second reason the SR-72 feels like it breaks physics. It is not pushing a normal engine beyond its limits. It is using an engine that was built specifically for a world where Mach 5 is normal. And without this engine system, nothing else about the SR-72 would matter. If the engine makes Mach 5 possible, heat is what usually makes it impossible. At hypersonic speed, the problem is no longer just airflow. It is temperature. Air compresses so violently against the aircraft that it heats up before it even touches the surface. By the time it reaches the skin, temperatures can climb past 1,000 degrees Celsius. That is hot enough to weaken most metals and destroy the adhesives and coatings used in modern aircraft. This is why the SR-71 had to rely on tricks like fuel cooling and special alloys. Even then, it leaked fuel on the ground because its structure had to expand in flight, and that aircraft flew at Mach 3, not Mach 5. The SR-72 cannot rely on tricks. It has to survive this heat directly. This is where material science becomes just as important as engine. The aircraft is believed to use advanced ceramic composites and high-temperature carbon materials that behave different under extreme heat. Instead of weakening, they become more stable. Instead of expanding unpredictably, they manage stress through design. Heat is no longer something the aircraft tries to avoid. It is something the aircraft is built to tolerate as a normal condition. But even materials have limits. Heat still has to go somewhere. So the SR-72 likely uses internal pathways to move heat through the structure instead of allowing it to concentrate in one place. Think of it as circulation instead of insulation. Heat is guided across the airframe, spread out, and managed rather than fought. This also reduces the infrared signature. An aircraft glowing in one spot is easy to detect. An aircraft that spreads its heat carefully becomes much harder to track, even at extreme speed. And this is where the design starts to feel less like an airplane and more like a system built for a completely different environment. Because at Mach 5, the sky is no longer a friendly place. It is closer to flying. Through a furnace, the SR-72 survives not because it avoids that furnace, but because it was designed to live inside it. Going fast is one problem. Staying in control while going that fast is another. At hypersonic speed, airflow becomes unpredictable and violent. Small changes in angle create enormous forces. Surfaces that work perfectly at lower speeds suddenly become unstable. Even tiny design flaws can turn into dangerous stress points. This is why most aircraft are never meant to maneuver at extreme velocity. They can go fast in straight lines, but turning, climbing, or adjusting direction becomes risky. The SR-72 cannot afford that limitation. It is not designed to sprint in a straight path and hope nothing goes wrong. It has to maneuver, adjust course, and remain stable while air pressure is trying to twist and bend every surface. Traditional fighters deal with this using brute force control authority, pushing harder on control surfaces to fight the airflow. At Mach 5, approach simply does not work. The SR-72 uses a different idea entirely. Its control systems rely heavily on prediction rather than reaction. Sensors monitor airflow constantly, and onboard computers model how that air will behave moments before it actually does. Control adjustments happen before instability forms. The aircraft does not wait for turbulence or shockwave shifts to affect it, anticipates them. This makes the aircraft feel less like it is flying through air and more like it is navigating through a constantly shifting pressure field with advanced awareness. The shape of the airframe also plays a huge role here. Every angle, every edge, and every surface is designed to keep shockwaves stable and predictable. Instead of fighting chaotic airflow, the SR-72 keeps the airflow organized around it. Stability comes from design, not brute force. This is critical because maneuvering at hypersonic speed is not just about control, it is about survival. If the aircraft loses stability for even a moment, the forces involved are so large that structural damage could happen instantly. The SR-72 avoids this by never allowing that moment to occur. Control is continuous, smooth, and calculated long before problems appear. This is another reason the aircraft feels like it ignores traditional limits. It is not relying on stronger parts or heavier structures. It is relying on smarter interaction with the air itself. At Mach 5, control is not about muscle, it is about prediction. Speed in air combat has always mattered, but only in short bursts. Fighters could sprint to intercept or escape, then had to slow down before heat, fuel burn, and stress caught up with them. That limitation shaped how missions were planned for decades. Routes were chosen carefully. Timing had to be precise. Aircraft had to work around threats instead of through them. The SR-72 changes that completely because it can sustain hypersonic speed. It does not treat velocity as something temporary. It treats it as the normal way to operate. That changes the entire timeline of a mission. Distances that once took hours can now be covered in minutes. A defended region that required careful planning can be crossed before the defense network fully understands what is happening. This matters because modern air defense systems rely on time. Radar must detect, computers must classify, command centers must decide, missile systems must calculate an intercept path. Each step depends on the one before it. When an aircraft moves this fast, those steps begin to break down. The system is still processing the first signal when the aircraft is already somewhere else. The SR-72 is not sneaking past defenses, it is outrunning their ability to react. This allows completely different mission profiles. Instead of plotting careful routes around danger, the aircraft can move straight through contested airspace. Instead of waiting for perfect conditions, it can force the timing of the encounter. Speed becomes initiative. It also changes survivability. Missiles rely on predicting where a target will be. At hypersonic speed, prediction becomes extremely difficult. By the time a missile is launched, the SR-72 may already be far outside the original intercept zone. The faster the aircraft moves, the harder it is to trap. And because the aircraft returns home, this advantage can be used repeatedly. It is not a one-time event like a hypersonic weapon. It is a reusable platform that can gather intelligence, strike targets, or relay information again and again. This is what makes sustained speed more powerful than top speed. It changes how the battlefield works. Modern air defenses were built for fast aircraft, but not for this kind of fast. Radars still need time to track. Missiles still need time to predict. Command centers still need time to decide. The SR-72 removes that time. At Mach 5, the aircraft crosses hundreds of miles in minutes. By the time a radar confirms a missed contact, the SR-72 is already somewhere else. By the time a missile calculates an intercept, the prediction is already wrong. The entire chain of detection and response starts to fall apart. This is why speed becomes a weapon. The SR-72 does not rely only on stealth. It relies on moving so fast that defenses cannot react properly. Systems built to keep aircraft out simply cannot keep up with something operating in this speed range. That is what changes the future of air power. The SR-72 does not defeat defenses by hiding. It defeats them by being too fast for their logic to work. If you enjoyed this video, don't forget to like and subscribe to the channel. Thank you for watching.